It's a very ubiquitous and all-pervasive feature of our experience of the physical world that we seem to be able to remember the past and affect the future, but not the other way around. How nice it would be if I could go back to that party the other night and correct that awful social gaffe that I made. But I know I can't. How nice it would be if I could go forward in time and learn the outcome of tomorrow's horse race and place my bets accordingly. But I know I can't. So this consciousness that we can remember the past and affect the future, but not vice versa, seems to be a really basic and fundamental aspect of our perception of the physical world. So basic that we rarely bother to think about it. A related point, which is not quite the same, is that if I am shown a movie of some domestic event, like say, I don't know, a cup falling off a table and the milk spilling out of it, I can usually tell whether that movie is being run backwards or forwards. Okay, so why should anyone think that this is a problem? Well, the difficulty is that, with one very small exception, which I won't go into unless anyone wants to ask me about it, the basic laws of physics, as we know them, seem to make no distinction between the forward and the backward direction of time. Let's think about the most basic laws which we know, which are the Newton's laws of motion. Can I have the first slide, please? Could you display the first slide, please? I'm not actually seeing it. Wait a moment. Oh dear. No, yeah, but slide one. Yeah, thank you. To slide two then, please. Slide two. Can you put up slide two, please? Yeah, great. Okay. Now, if we think about Newton's three laws, remember that his first law says that any body either stays at rest or moves uniformly, provided that it's not acted on by any force. And clearly, that law makes no reference to the direction of time. Similarly, Newton's third law says that every action has an equal and opposite reaction. Again, no mention of the direction of time. So if the direction of time comes in anywhere in Newton's laws, it must be in the second law. So you know that Newton's second law says that force is mass times acceleration. Well, force might be something like gravity, but again, there's no mention of the direction of time there, nor is there in the notion of mass. What about the notion of acceleration? Well, the acceleration is the rate of change of the velocity, v. What happens to the acceleration if time is run backwards? Well, if time is run backwards, then the velocity is reversed. So let's think about, say, a merry-go-round. So I'm standing with my back against the wall of the merry-go-round, and the merry-go-round is rotating clockwise. Now I will feel on my back a push. And the reason for that push is that, in fact, by standing next to the wall of that merry-go-round, which is turning, I am actually being accelerated towards the center of the merry-go-round. And according to Newton's second law, then that means that I must feel an appropriate force. So I feel the force pushing against my back. Now what happens if we reverse the direction of rotation of the merry-go-round? So it's now rotating anti-clockwise. Well, the velocity is reversed, but I will still feel a force on my back. I will still be accelerating towards the center of the merry-go-round. In other words, the acceleration has not been changed by reversing the direction of time. So that means then that Newton's three laws, which are the basis of classical mechanics, work just as well backwards as forwards. Okay, you say, well, that's fine, but there are other kinds of basic phenomena in physics, say electromagnetism. What about magnetic fields? So if I have a magnetic field, say in the upward vertical direction, and I have an electron in that field, then it will circulate, let us say clockwise, I'm not sure if that's right or not, but let's say clockwise around the magnetic field. If I now change the direction of time, it looks as if the electron will be circulating anti-clockwise. So it looks as if I should be able to tell. However, the problem is, unfortunately, where does the magnetic field come from? The magnetic field comes from, for example, currents flowing in some kind of circuit. If I reverse the direction of time, then I reverse the direction of those currents, and the electron will still appear to go around clockwise. So we can't tell again. Well, you might, those of you who know about quantum mechanics might ask, isn't there some direction of time implied in quantum mechanics? Don't we start by preparing a system, let it run, and then measure it at the end of the day? And isn't that process somehow asymmetric in time? And unfortunately, the answer is no. This is a much more complicated question, but I can assure you that there have been some very interesting papers written on that subject. And if you look at it correctly, the answer is that quantum mechanics really does not, contrary to what you might think, distinguish the forward and backward directions of time. So let's see. Can we go to the next slide, please? Slide 3. Thank you. Well, there is a related question, which is it correct to say that the past causes the future? Well, we might think intuitively that was right, and let's see if we can actually make an argument for that using Newton's laws of motion. A very standard kind of textbook problem is one in which you have a cannon, the blue object there, which is firing a cannonball, the red object. And typically, if a textbook asks you to solve this problem, what it'll do is it will give you the initial position and velocity of the cannonball, and then it will ask you to calculate the trajectory and eventually end up at the final position and velocity. And it'll ask you to calculate those. So it's certainly true, you can do that. If we know the initial position and velocity, you can determine the exact trajectory, and in particular, you determine the final position and velocity. And this idea impressed people a lot, particularly when Newton's mechanics was somewhat of a novelty. And so it's very tempting to think that the initial conditions cause the subsequent motion. And this is the basis of a famous thought experiment due to the famous early 19th century French mathematician and physicist Pierre-Simon Laplace. He said, let us imagine a demon whose faculties are so acute that he can actually learn the position and velocity of every particle in the universe. And moreover, he knows all the forces acting in the universe. Then that demon would be able to predict everything that was going to happen in the universe in the future. Everything would lie open to his gaze, I think he says. And many people have actually taken that argument as an argument against the idea of free will. I just raised my hand just now, but well, I thought I did it voluntarily. I thought I was exercising my free will. But no, if you follow Laplace's argument, then this was a result of the position and momentum of every atom in the universe a few minutes ago. So it cannot have been my free will, or at least that's the crude version of the argument. But is that argument actually right? Let's forget about free will for a moment. Let's just ask, is the initial stage of the argument actually right? Well, technically, Newton's second law is of second order in time. So what that means is that we actually start from the final position and velocity and infer the trajectory backwards and arrive at the initial position and velocity. Or in fact, we can start from an intermediate position of velocity and infer both the initial and the final positions. Or go to many other pieces of information which will allow me to infer the whole trajectory. And so there seems no good reason to suppose that it was the initial position and velocity which determined or caused the final one, rather than vice versa. So this seems a bit of a dilemma. We can't find anywhere in Newtonian mechanics, or for that matter, in electromagnetic theory or quantum mechanics, any basis for our idea that time flows in one direction only. So can I have view graph 4, please? Can you show view graph slide 4, please? Thank you. Well, in the early 19th century, there's a group of very brilliant physicists and mathematicians, many of them French or German, who worried a lot about this problem. And they eventually came up with a quite different way of looking at the direction of time. They said, let's imagine, for example, a gas which is confined to a part of a larger volume. That's the top diagram there. At a given time, I pull the handle and pull out the partition which is separating the two halves of this volume. When I do this, the gas will expand and fill the whole of the volume. Yeah, thank you, that's right. And I know that however hard I may try, if I don't do something drastic to the container, say, there's no way that the atoms of the gas are going to by themselves get back to the state they were in the upper diagram. And they're all going to spontaneously collapse into the left-hand side or the right-hand side. Why not? It's basically a matter of counting the number of states possible for the gas. Could we go on to slide 5, please? Thank you. This, as you can see, these slides were first made up for an American audience, and in an American audience, even of high school students, I can usually take for granted that they've all taken driving lessons. Now, I imagine that not all of you in Kerala have actually taken driving lessons, but I think you can probably nevertheless appreciate this argument. So suppose you were taking a driving lesson and the instructor takes you to the school car, which is parked by the curb, the sidewalk. That's the red block there. And he tells you to try to drive the car out into the road. You don't usually have too much difficulty doing that. But then at the end of the lesson, the instructor tells you to try to park the car again by the curb. And that you find, at least if you're a typical learner driver, you find that really quite difficult. Why? Well, it's rather straightforward. When you were getting the car out, you had a large final space available. It didn't really matter exactly where you went in the road. When you came back, it matters a lot that you get into exactly that space. In other words, you have a small final space. Now, these French and German physicists in the early 19th century generalized this idea to say that you could introduce a concept of disorder which had to do with the available space or the number of available states for your system. They, for a technical reason, they didn't make it just proportional to the space itself or the number itself, but rather to the logarithm of that number. There's a technical reason for that. And they call the concept, which they invented in this way, the entropy, and they denoted it with the symbol S. So the entropy then is a measure of disorder. And there's a famous formula which is usually associated with the name of Ludwig Boltzmann, which says that the entropy is a constant times the logarithm of the number of available states. And if you look at it this way, it looks as if, in some sense, it should be natural that the entropy should always increase in time, because it's easy to get from a small space or a small number of possibilities to a large one, and very difficult to get back again. And so this leads us then to the famous second law of thermodynamics, that the entropy always increases with time. And many textbooks, certainly the less careful ones, will give you the idea that this is the origin of the asymmetry with respect to time. Well, first sight, that looks convincing. And in fact, a lot of the textbooks just stop there. Then you think, wait a moment. Why are we assuming that it's the initial states which have a high degree of order, and that disorder follows later from that, rather than vice versa? Okay, let's go on to the next slide, please. Thank you. Let's imagine the following experiment. I have a closed box, a closed room, which contains what I call a mechanical shuffler. So most of you, I think, are familiar with the idea of shuffling a deck of cards. But we're not going to do it by hand. We're going to allow this machine to do it. So the machine is going to shuffle the cards, and going to do it, say, every 5 minutes or so. And we also install a camera in the closed room. The camera has two functions. First of all, it makes sure that no one somehow gets into the room. But secondly, more importantly, it displays the order of the cards after each shuffling process. Well, we can imagine that we start with a nice ordered arrangement, ace of spades, king of spades, etc., etc. After the first shuffling, this will be somewhat disordered. As the shuffling goes on, it'll become more and more disordered. So fair enough, it looks as if the disorder, the entropy, if you like, is in fact increasing in time. And now you say, wait a moment, the inverse of a shuffling process is itself a shuffling process. So suppose that I look at the camera at a particular moment, and I see, and admittedly, it's unlikely, but admittedly, suppose I see that the order is in fact that ace, king, queen, jack there, the exactly ordered sequence. Well, of course, my first thought would be that someone has crept into the room by, undetected and arranged the cards in that way. But suppose that we actually have the camera is sufficiently all seeing that we know that's not true. Then we can ask ourselves the question, okay, before 12 o'clock, when I actually looked at the camera, the machine was still going through its shuffling processes. What is the state of the cards earlier on? Well, as I say, the inverse of a shuffling process is itself a shuffling process. So we have to conclude that not only the state after 12 o'clock is more disordered, but the state before 12 o'clock is equally disordered. So we have not really got ourselves an explanation of the direction of time. One more, next slide, please. Okay, so at first sight, you might think this means that the notion of the increase of entropy with time, and therefore the second law of thermodynamics, has to do specifically with the fact that as human beings, we can prepare an initial situation, but we can't, as it were, retropair a final situation. So it has something to do with our human capabilities. Then you figure, no, that can't really be true, because there are a whole lot of processes in the natural world where we can still work out the direction of time and work out whether the movie is being shown forward or backwards, despite the fact that there are no human beings involved. For example, let's imagine we have a rock perched precariously at the top of a cliff. In time, there will be erosion takes place and the rock falls off the cliff. So it'll fall off, it'll fall into the lake at the bottom. As a result, it's falling into the lake. There will be waves which are radiated out to infinity. And at the end of the day, the rock will just end up on the bottom of the lake. If that movie was shown backwards, then what would happen is that the rock would rise up from the bottom of the lake, the waves would converge in from infinity, the rock would spontaneously climb up the cliff and reattach it at the top, itself at the top. And we know that's not something which happens in real life. So in other words, the arrow of time still seems to work even when there's no reference whatever to any human beings involved. So how do we explain it? Okay, next slide, please. Well, one person who worried a lot about this problem was the great Austrian physicist Ludwig Boltzmann. This is a picture of his tombstone in the Central Friedhof in Vienna. And you see that above his head there is inscribed this famous formula, S equals K log W, which is a bit ironic because as far as the historians know, Boltzmann himself never actually wrote down that formula. It was written, he certainly had all the ideas there, but he did not actually write down this formula. But anyway, he had a very, very interesting notion, which was actually about 150 years ahead of its time. And if we go to the next slide, we can see what that notion is. Okay, so suppose that we indeed take it for granted that, as it were, the most natural state for any system to be in is its most disordered possible state. Then let's think about the universe in our neighborhood. The universe will in general tend to its most disordered state. But occasionally we know, and this is something which Boltzmann actually calculated in great detail, we know that occasionally there will be fluctuations away from that most disordered state, or in other words, the entropy will fluctuate away from its maximum value, to fluctuate to a lower value. But that fluctuation won't last very long. It'll soon come back to its most disordered possible state. So suppose that we are actually sitting on the right-hand part of this bump or this dip in the curve. Then we will automatically see entropy increasing in one direction and not in the other. And so we will define then the future as the direction in which the entropy is increasing. Suppose we had been on the other side of the curve, on the left-hand side of the dip. Then we would have seen the entropy increasing towards the left. And then we would have identified the leftward direction as the direction of the future. But, well, this is nice so far. But then, of course, one can raise the question, and Boltzmann did raise the question, well, but why should we happen to be living in just this very peculiar and untypical moment when there is this large fluctuation? And he then gave an answer to that problem, which is essentially a 150-year anticipation of what nowadays is called the Theanthropic Principle. His answer was, well, it turns out that if we were living, or it may turn out, if we were living in one of these regions where the entropy is at its maximum value, then, crudely speaking, physics would not work the way we know it. Chemistry certainly couldn't work. Biology wouldn't work. We would not exist. In other words, the reason why we're living in this very untypical region of space-time is that because if we were living anywhere else, we would not be around to ask the question. As I say that, and nowadays that idea has come back with a vengeance in some kinds of argument to explain why the fundamental constants of nature, like say the electric charge or the electron mass, have the values they do. The argument is basically that if they didn't have the values they do, we would not be here to ask the question. Well, unfortunately, that notion was perhaps quite plausible in the time of Boltzmann. Nowadays, however, we have space. Hello? No, nowadays we have space telescopes and satellites and whatnot, and we can actually see out into the universe many orders of magnitude further than Boltzmann could. So it doesn't, and it looks as if it's not just our neighborhood which has this the properties that time runs in one direction only. It looks as if that works way out to the most distant quasars that we can actually see. In other words, the direction of time does not seem to be, in any sense, special to our position in the universe. Let's go on to discuss, next slide, please. The various possible hours of time, which have been discussed in connection with this question. There's, first of all, the psychological hour of time, which I've mentioned already. It says we can remember the past and affect the future, not vice versa. Biological hour, plants and animals seem to start small, grow bigger, finally die. It's the electromagnetic hour of time. It's actually not entirely a trivial observation. It's not just, say, man-made objects, which, like light bulbs, which can emit radiation, but the stars also emit radiation rather than absorbing it. We've already mentioned the thermodynamic hour of time, the statement that disorder or entropy increases with time. Finally, there's the so-called cosmological hour, which basically says that the universe is expanding rather than contracting, and therefore you can define, if you like, the hour of time or the forward direction of time by the direction of expansion of the universe. So how could these be related? Well, I think in the case of the psychological and biological errors, the connection seems rather natural. There's no logical contradiction to the idea that I might be able to remember the time when my hair is even whiter than it now is, and I'm basically doddering towards my grave. And I should be able to affect the time when I was small and yelping in my mother's arms. But somehow it looks like there has to be a rather natural reason why that doesn't work, although we don't, of course, understand in great detail why that is. What about the biological and electromagnetic errors? Well, there I think there's a fairly direct connection, because how does biology work? Well, basically, plants or animals absorb energy from sunlight and turn it into chemical energy. That's the way that plants get bigger, basically. If the sun were not radiating energy, but rather absorbing it, that of course would not work. So that at least looks a fairly natural connection. The electromagnetic error, again, can be regarded as a special case of the thermodynamic error. If you work out a reasonable definition of disorder, then the state in which the radiation has been emitted and is basically gone to infinity is more disordered than the state in which the energy was confined to the star. Finally, what about the cosmological arrow? That's a more difficult one. Let's go on to the next slide, please. Most models, the generally accepted standard Friedman-Robertson-Walker model of cosmology, whatever the details of it, seems to agree about the past. So it does seem that if we extrapolate the laws of physics, as we know them, backwards in time, then eventually we will get to a point where we find that inexorably matter is both infinitely dense and infinitely hot. And that is what is usually called the hot Big Bang. Unfortunately, now you might think that it was natural that the disorder should be very low at the hot Big Bang. But in fact, common sense really says rather the opposite. Since it's very hot, and then you would think that at first sight, the universe at the hot Big Bang should be very disordered. That turns out not to be the case. The universe is in fact incredibly well ordered at the hot Big Bang. So incredibly ordered that you have to use powers of 10 to the 120th or something to get a quantitative measure of it. So the real heavyweights in this area, people like the late Stephen Hawking and Roger Penrose, who just got the Nobel Prize, they argue with one another about this. Some people claim, and I think Stephen Hawking would have claimed, that he does have a reason why disorder should be low at the small end. But other people, and quite respectable people in cosmology, disagree with that. So that seems to be still a possibly open question. Let's go on briefly, but not ask. Well, okay, the past is difficult. What about the future? And according to the standard model, there are three possible futures of the universe, and they correspond to whether a certain quantity, which is basically the density, the average density of the universe expressed in appropriate units, whether that is less than 1, equal to 1, or greater than 1. If that quantity, capital Omega, is less than 1, then the universe will go on expanding forever. If it's flat, which might seem very improbable, but it turns out arguments why it's not all that improbable. If the universe has Omega exactly equal to 1, then it will expand out to, crudely speaking, would eventually tend to a sort of constant value. Finally, if the universe is closed, then it will expand to a maximum value, but then contract again. And Eventually, in some sense, the early history will be reversed, and we will end up with what is sometimes called the hot big crunch. It's the inverse in time of the hot big bang. Next slide, please. So let's ask the question. Suppose that we indeed do live in a universe which is closed, so we expect this to take place, this to happen. Once we get past the maximum size of the universe and it starts contracting again, will disorder be increasing or decreasing? And if just, and assuming that still humans are around, it seems improbable at that time, which way would they actually see the future? And believe it or not, the heavyweights in this field, in cosmology, still disagree on this vital point. So I don't think we can really claim that there is universal agreement that cosmology does explain the error of time. And it seems to me that it is, in some sense, still a very deep mystery. And finally, I think this is the last slide, please. Yeah. Let's just raise a rather different question. Let's suppose that indeed we find, or everyone agrees, that cosmology, considerations of cosmology do explain the error of time, as it were, in the large. Could the error of time nevertheless reverse itself locally and temporarily? And what should anyone think of that notion? Well, it turns out there's a very famous series of experiments which have been carried out in the last few decades. Technically, for any of those, some of you might know, these are called the so-called EPR Bell experiments. And the way they run is roughly as follows. You have an atomic source which will emit pairs of particles, usually photons, particles of light. And these photons are then directed into a switch which will switch them into one of two measuring devices. And that happens for both the photons at each end. And these measuring devices measure different properties of the photon. Now, there is an experimental fact that the observed, so the raw data in the experiments is the correlation between the results you got at one end of the laboratory and the results you got at the other end. And the laboratory in question could be kilometers wide, or even hundreds of kilometers these days. So these are very, very long distances you're talking about. Well, the interesting thing about the raw data is, well, they are consistent with quantum mechanics, but what is more in present context, what I want to emphasize, is that they are inconsistent with any theory which embodies three properties. The first one is objectivity, the idea that physical systems have properties whether or not you're actually measuring them. The second idea is locality, the idea that causal influences can't propagate faster than the speed of light. And the third property is what I've sometimes called induction, but I think the error of time is a better idea, better name. The idea that the future cannot influence the present or the past. We use that because we implicitly argue that the way I decided to do the measurement at the two ends of the laboratory cannot affect the way in which the photons are emitted from the atomic source in the middle of the laboratory. Is that true? Could the outcome of the measurement somehow propagate backwards in time and affect the initial state? What? Well, it seems if formally that's okay, and some people have developed descriptions which have that property. The really $64,000 question, I think, is can you reconcile that, in some sense, that reversal of the arrow of time at the locally and temporally with the macroscopic second law, which we do know holds to pretty well in real life. Just one small observation, which I think is quite amusing. Would that affect the arguments about free will? Well, I think it might. As I say, I raised my hand. I thought I was doing it by exercising my free will, and the advocates of Laplace will tell me, no, that's not right, because it was the behavior of the molecules 10 minutes ago which determined that I was going to raise my hand. But I say no. The fact that I raised my hand now determined the state of the molecules 10 minutes ago. The question is, can we make a self-consistent picture out of that? And this is something which has always fascinated me. And I don't know the answer to that question, but I am trying to think about it. So finally, let me make a general remark. If you look back at the last 500 years in physics, you see that just about every major revolution in the field has involved the falsifying or the rejection of some idea which until that point had seemed absolutely crude common sense. It was common sense that the sun goes around the earth until Copernicus told us otherwise. It was common sense that the relative order and time of two events cannot depend on the motion of the person who observes them, until Einstein told us otherwise. It was common sense that microscopic objects have properties even when we don't look at them, until Heisenberg told us otherwise. If and when we get a major revolution in the foundations of physics, and I'm fairly confident that we will get such a revolution sometime in the next 100 or 200 years, my own bet is that whatever else that revolution involves, it will involve a revolution in our way of thinking about the arrow of time. If you ask me what is that new approach to the arrow of time going to be like, the only answer I can give you is the answer which I believe the jazz musician Louis Armstrong is said to have given to someone who asked him where jazz was going. And his answer was simply, man, if I knew where jazz was going, I'd be there already. Thank you.
Sir?
Yeah.
Can I stop sharing the presentation?
Yeah. Is that okay? Yeah.
I request the participants to post your queries in the chat box. Sir, I will read out some of the queries which we have got already.
Okay.
Nasif Jinan is asking, is time travel possible through wormholes? What do you think about it?
Yeah, that's something I think which a lot of people have wondered. I tend to think that we are not only, that right now, we are not only extrapolating quantum mechanics well beyond the level at which we have experimental evidence for it, but we're also extrapolating general relativity far beyond the level at which we have direct evidence. Of course, one has to say that there's some very rather nice direct evidence for at least parts of general relativity, for example, the work for which the three people just got the Nobel Prize. But we certainly have not explored experimentally general relativity to at the level where it would give rise to wormholes. And I'm personally inclined to doubt that wormholes are a physical reality, that we can ever get them to exist in real life. So that in some sense would be the cop-out answer your problem, because you would still ask, well, let's assume for the sake of argument that wormholes do exist. Would they enable us to travel in time? Again, my suspicion is no, but I can't really prove it. So I can't give any kind of rigorous argument which says that, for example, entities with a large degree of biological organization like ourselves would not behave in wormholes the way that general relativity says. So basically the answer is I don't know.
Thank you, sir. One question from Hyson Thomas. As time runs, the entropy increases. If take the case of universe, this implies everything was in a highly ordered situation in the long past. Is there any scientific explanation for the cause of this highly ordered state of the universe?
No, basically, as I say, that's what the heavyweights argue about. If you're interested in this question, I think a very good book to look at, which discusses actually it's a general discussion of the arrow of time, but it does put a lot of attention to this particular question. There's a book by Hugh Price. That's H-U-W, Price. He is actually a philosopher, very interested in the foundations of physics. He works at Oxford University. And the book is called Time's Arrow and Archimedes' Point, I think. Time's Arrow and Archimedes' Point. And he discusses this question of whether cosmology or other basic physics can provide an explanation of the fact that entropy was so low at the beginning of the universe. And crudely speaking, it comes out with the conclusion that it can't. And I think I would tend to go along with that conclusion.
Thank you, sir. Next question is from Eldo Sunny. Time does actually shows fluctuation in space as compared to Earth. So does it mean time is actually influenced by gravity and in turn influences its speed?
I'm sorry, could you just read that again? I didn't catch all of that question.
Eldo is stating that time does actually shows fluctuations in space as compared to Earth. So does it mean time is actually influenced by gravity and in turn influences? He's asking whether time is actually influenced by gravity.
Okay. Yeah. Well, within the general framework of Einstein's general relativity, the answer is yes. That is that, for example, if I take a clock and displace it to a point where the gravitational potential is very different from what it is here, we would expect it to run at a different rate. There is some indirect experimental evidence that is correct. There was an experiment done actually quite some decades ago now at I think MIT, where they could measure time extremely accurately, and they could verify that clocks at different positions, different heights in the Earth's gravitational field do actually run at slightly different rates. And this is, it's actually quite interesting that This is now a major consideration in designing things like the GPS, the Global Positioning System. With the accuracy with which we can measure time is now so incredibly fine that quite literally, if I have a clock which is sitting on my table here, I take it off and put it on the floor, I can actually measure, in principle, the difference in the rate at which it's ticking. So yeah, I think the answer to the question is yes, at least so far as we believe general relativity, and this has been, let's say, at least to an extent, confirmed experimentally.
Thank you, sir. Next question is, Big Crunch, is it a future possibility?
Well, again, if we believe the standard cosmology, the so-called Friedman-Robertson-Walker cosmology, then the Big Crunch will happen if the density of the universe expressed in appropriate units is greater than 1. As to the experimental evidence as to whether it is greater than 1 or not, I think one would probably say that in general it's probably against it. It seems more likely that the dimensionless density is either equal to 1 or considerably less than 1. But so in which case we will not in fact get a big crunch. But these things are still very much up in the air, and it could be that a new set of experimental observations tomorrow will just up in that point of view.
Thank you, sir. Jissa Jacob is asking, can we talk about time in a static universe?
When we talk about time in a static universe, well, people did for many, many years before Hubble's discovery that the universe was expanding. I don't think there are any special conceptual problems about talking about time in a static universe. So I think the answer was yes.
Okay, sir. Next question is time travel possible through quantum realm?
Through quantum, sorry?
Quantum realm.
Oh, through the quantum realm.
Yeah.
Not that we know of today. However, I think we have to say that quantum mechanics is now pretty much 100 years old, and it was only really since, well, let's say the mid-80s or perhaps a little later that we realized some of its potential for, if you like, engineering applications. That is the huge field which now exists, which is called quantum information. Before the mid-80s, basically, there was no quantum information because people were simply, it did not occur to people that you could do things with quantum mechanics that you couldn't do with familiar classical physics. Quantum information has revealed quite a lot of things, particularly in the area, say, of quantum computing or cryptography, which we can do. And it's conceivable that we will eventually find that another thing that we can do is time travel. But right now, at least, I think we don't really have any very definite ideas about that.
Thank you, sir. Next question is, how deeply is time connected with causality?
Very, I'd say, very deeply. That is, it seems to be a really rather fundamental principle of our perception of the world. What I think the philosopher Immanuel Kant would have called this a piece of synthetic a priori knowledge. That is, a piece of knowledge which you can argue, as it were, from bare principles is right, but which nevertheless provides you with some non-trivial information about the world. I think Kant would have said that the idea that causality has to propagate only forward in time is one of these so-called synthetic a priori statements. So people who have investigated theories in which the direction of causality is reversed. I find it difficult to really judge the significance of those theories. They, almost by definition, they don't enable you to predict anything. That would be contrary to the object of the exercise. But right now, I would say that these theories about so-called retrocausality and so forth don't really have any, as it were, substantial content. That is, by themselves, they don't really tend force you to look at the world in a way different from one that we do in everyday life when we're seeing is that the world does propagate all the time. But again, that may change. Who knows?
Thank you, sir. Next question from Alan. Some recent particle experiments show entropy reversal. So, if this happens, what will be the implications, especially how will it affect the universality of quantum mechanics?
Okay, I'm not clear what this question is referring to. There are two kinds of experiments that it might be referring to. One is an experiment which I think was first conducted in 2014 in a large particle accelerator. The other is a set of experiments which have been conducted over the last few years, more or less tabletop experiments, which involve, say, colloidal solutions and things like that. If you're referring to, if the question is referring to the first, or let's do the second one first, actually. If the question is referring to the second set of experiments, what these essentially show is that if you only study a small region of the universe for a small time, for a short period of time, then indeed there can be fluctuations in which the entropy of that small region does decrease. That really is not in any contradiction to the classical ideas of people like Clausius and Boltzmann and so forth. It's not really, I think, in opposition to our fundamental ideas of thermodynamics. The first set of experiments, the other set, refers to these high energy collisions, and what they do seem to show rather directly. Yeah, I mean, people have suspected this for 50 years, but these experiments show rather directly that there are some physical phenomena which occur at the level of elementary particles, which in fact do have a well-defined direction of time. So that's contrary to what I've been mostly talking about, and I did make a qualification of that at the beginning of my talk. That was what I meant to exclude. But yeah, so it is not in fact true that all the fundamental equations of physics are insensitive to the direction of time. The real question is, we've only discovered that phenomenon in experiments conducted in high energy accelerators and so forth. As far as we know, it has no obvious consequences at the level of ordinary life. Now, it is conceivable it has some consequences at the level of cosmology, and therefore indirectly it might address this question. But I think most people who thought about this question seriously think probably not. That sometimes the feel is not right. The nature of this violation in elementary particle physics is just not the kind of violation that we really need to explain the everyday error of time. Again, could be wrong, but as I say, that I think the feeling I would tend to share that feeling.
Thank you, sir. Next question is there any negative energy exist which can make a scalar speed a directional quantity?
I'm sorry. Does negative energy exist which could make what?
Which can make a scalar speed a directional quantity. Speed
Oh,
is scalar. Will it become directional quantity when negative energy exists?
I'm very slightly puzzled by that question. Um, the I think I think I'll give a quick answer to that question, which might be sometimes a bit of a cop out, which is that if we mean what we usually mean in mathematics or physics by a scalar quantity, and we mean what we usually mean by a vector or spinor quantity, then I think the existence of any so-called negative energy is going to be rather irrelevant to that distinction, right? So I think the answer is no. But maybe that was not the question I meant. I'm not sure.
Next question is, like particle has antiparticle, will there be a universe in which time runs backward?
Well, as you may know, there's a set of ideas which have been propagated. I think it's probably fair to say largely by popular writers on physics rather than by professional physicists themselves, which goes under the name of the multiverse. And the idea is that the universe we actually experience is only one of a vast number of universes which, at least according to the laws of physics understood in the most general sense, are possible. For example, there could exist universes in which let us say, the mass of the electron relative to that of the proton is rather different from what it is in our universe. That's a rather trivial example. Such a universe, if it did exist, would almost certainly have properties quite unlike ours, and in particular, it seems unlikely that human life could exist in it. But you can go further, yeah, sure. You can go further and speculate that there might be universes in which, so far as we can compare the arrow of time with ours, it would appear to run backwards. Then, of course, you do run across the rather thorny problem of, okay, suppose in some sense, in principle, these different universes, these multiverses exist. Would we ever be able to get in any sense in contact with them? Because it's only if we could get in contact with them that we can really raise the question whether their arrow of time is in the same direction of ours or not. So these ideas, I think, are highly speculative. One can't say that one can disprove them. All one can say is that we certainly don't need them right now, and therefore, by the principle of Occam's razor, I think most practicing physicists would regard them as somewhat irrelevant.
Sir, here's a question from our YouTube watchers. Is it possible to meet our future with fast time?
Is it possible to meet our future
With fast time.
in past time? I'm sorry, I don't think I got the last two words. Is it possible to meet our future in past?
With fast time. Fast.
With,
F-A-S-T, fast time.
Okay, sorry, got it. Right, thank you. Is it possible to meet our future with fast time? In other words, could we somehow speed up the arrow of time, or the progress of time, so as to access the future? Well, we certainly don't know how to do it right now. Again, I think one can't be too conservative. Most of the a huge amount of what we regard as standard physics today would have seemed totally absurd to physicists even in, let us say, in the 17th century, let alone in the 13th century. All I think we can really say is that we certainly don't know how to do it right now, and I don't think we really would know where to look for ways to do it. But again, one never knows. It's entirely conceivable the future revolution in the foundations of physics could give us that opportunity.
Thank you, sir. Here's another question. What happens after I trapped into black hole and then it going to singularity?
I'm sorry, you're going to have to read that to me again, I'm afraid. Could you reread that question?
Sir, what happens after I trapped into a black hole and then it going to singularity?
What happens if light falls into a black hole? Well, I'm afraid.
What happens after I trapped into black hole and then it going to singularity?
Well, we don't know. I think one does get a difficulty here. Even if we accept that the conclusions which people like the late Stephen Hawking and Roger Penrose drew from Einstein's general theory of relativity are formally correct. That is, that the mathematics leads or might lead inexorably to the so-called black hole phenomenon. That is, crudely speaking, a surface over which the apparent directions of space and time are reversed. That's I guess a crude definition of a black hole. We can extend the mathematics beyond that point. I don't really think we can extend the physics beyond it. So in fact, it will not be at all trivial to see what happens when we, as we presumably will be able to do sometime hundreds of thousands of years from now, when we send the first spaceship into a black hole. I think we really don't know. However, I have to reformulate this slightly because, in fact, there's this peculiar phenomenon which occurs at the surface of a black hole. And incidentally, there's a very nice science fiction story by the late Pohl, which exploits this fact. If I'm on a spaceship and that spaceship appears to go through goes through the surface of a black hole, then I will not feel anything particularly special at that point. However, if I'm an observer back here on Earth, trying to track the progress of that spaceship, it will appear to, as it were, approach slower and slower, and it will never, in fact, fall into the black hole. This is one of the paradoxical things concerning black holes. So what we need to do, I think, is to take a very brave and foolhardy graduate student, put him in that spaceship, send him through the black hole, and then get him to figure out how to get out of it, get him to tell us what he experienced. I think this is going several orders of magnitude beyond what we know today.
So our chat boxes are overflowing with questions, but as we are running out of time, can we stop the interaction now?
Okay.
Or how long will you be able to continue with the question and answer session?
Well, yes, but I don't. They can send me an email, but I have to say I can't guarantee to. Hello. I have rather a lot of things.
Hello, pardon, sir.
Yeah, I say any of the people who would have liked to ask questions but don't have
Black hole.
no time to do so, they're welcome to send me an email with the questions, but I have to warn them that they may not get a very quick reply because I just have too many other things on my calendar right now.
Okay, sir. Then can we share your email in chat box?
Yeah.
Okay, sir.
Hello.
Is some of the participant interrupting? Does anyone want to ask anything? Hello?
Ma'am. Sir, any idea of time machines?
No, not really. I mean, I think I've said everything that I know about time machines in answers. There's not much in answers to the last few questions.